All right, so the last way to communicate enthalpy changes is by using potential energy diagrams. So the steps that we're going to use to make our potential energy diagram is we're going to write out a thermochemical equation. And for our diagram, if we have an exothermic reaction, then the reactants are going to be higher in potential energy than the products. However, if we have an endothermic reaction, then the products are going to be higher in potential energy than the reactants. And then last but not least, we need to make sure to label our diagram. So we need to label our change in enthalpy, the axes, and title the graph. So down below here are some oversimplified drawings of potential energy diagrams, and the main point of them is to get across that for exothermic reactions, the reactants are higher than the products in terms of potential energy, and your delta H, or your change in enthalpy, is going to be negative. And the reason why change in enthalpy is negative is because for exothermic reactions, heat is exiting the system, so heat is being released. For endothermic reactions, your products are going to have more potential energy than your reactants, and your change in enthalpy is going to be positive. Okay, and again, the reason is because endothermic reactions, heat is entering the system, so that's why your change in enthalpy is positive. All right. So first example here, the molar enthalpy of combustion of methanol is negative 725 kilojoules per mole. So we need to draw the potential energy diagram. All right, so back to our steps. Step 1, write a thermochemical equation. So that's where I'm going to go. So since this is the combustion of methanol, that is going to be where I start in terms of rating my reaction. Okay, so if you want to know the formula for methanol, you can find it on either page 4 or 5 of your data booklet. So methanol is here, so that's CH3OH. Okay. And then looking up the state of methanol, it is liquid. Now, since this is a combustion reaction, we're going to take our fuel, which is methanol, and react it with oxygen. So remember, oxygen is part of Hofbrinkel, so it's a diatomic element. And this is going to give us carbon dioxide and water vapor. All right, so now we need to balance our chemical reaction here. So we have one carbon going in, one carbon coming out. So those are balanced. For hydrogens, remember you always balance combustion reactions in the order of carbon first, then hydrogen, then oxygen last. So for hydrogen, we have 4 hydrogens, so 3 from here and then 1 from that last hydrogen. And then over on our product side, we only have 2 hydrogens. So we're just asking ourselves, what times 2 is equal to 4? Well, 2 times 2 is equal to 4. Okay, now for oxygen, we have 1 plus 2, so we have 3 oxygens on our reactant side, and we have 2 plus, so this 2 coefficient affects everything after it, so not just the hydrogen, but also the oxygen. So 2 plus 2, so we have 4 oxygens on our product side. Now, since there's a difference of 1 between our oxygens on our reactant side and our oxygens on our product side, I'm going to choose to increase the amount of oxygens by increasing the moles of methanol here. So I'm going to raise that to 2, which unfortunately is going to affect everything. So not just oxygens, but carbons and hydrogens as well. but that's okay, we'll figure it out. Okay, so that 2, it affects our carbons, our hydrogens, and our oxygens. Okay, so let's just go through again, balancing carbons first, then hydrogens, then oxygens. Okay, so we have 2 carbons on the reactant side. So I'm going to put a 2 over here to make sure I have 2 carbons coming out. Okay, for hydrogens, we had 4 hydrogens times by 2, so we have 8 hydrogens. So I'm going to make sure that I have 8 hydrogens on my product side by putting a 4 there. Now for oxygens, I have 2 oxygens here plus 2 oxygens here. So I got 4 oxygens on my reactant side, and then I have 4 plus 4, so I'm taking this 4, multiplying this by the 1 oxygen, so I have 8. Now since the difference between these two values is an even number, I'm going to balance the oxygens by changing the coefficient for our elemental oxygen. Okay, so how I'm going to do that is, since I have 2 oxygens coming from the methanol here, so I just ask myself, okay, 2 plus what is going to equal 8? Well, 2 plus 6. And 2 times 3 is going to give us that 6. So now everything's balanced. All right, now it wouldn't be a thermochemical equation if we didn't have an energy term, since this is a combustion reaction. Okay, and I can see that the molar enthalpy of combustion of methanol specifically is a negative value. That's my 2 hints here that my energy term is going to be on the product side because our molar enthalpy is a negative value for the combustion of methanol. Okay, but remember, this number only talks about methanol specifically, so it's molar enthalpy of a specific substance. However, when we write our energy term here, that is change in enthalpy, and it's not just for one substance, it's for the entire reaction. Okay, so we need to find the change in enthalpy using change in enthalpy is equal to moles times molar enthalpy, and in this case it's molar enthalpy of combustion of methanol. Okay, now since we weren't given a specific amount of methanol, the moles is going to come from the coefficient for methanol. The reason why I'm using the coefficient of methanol here is because my molar enthalpy is tied to methanol. So you want to make sure that both of these belong to the same substance. Oh, actually I'm going to use a different color here. And then our molar enthalpy of combustion was negative 725. So moles cancels out. So 2 times negative 725 is going to give us negative 1450. And that's going to be kilojoules. Okay, so like I said, because this is a negative value, that tells you, if your change in enthalpy is a negative value, that tells you that the energy term goes on the product side. Okay. Now, if I wanted to take into account sig digs here, So the value that we were given has 3 significant digits. So if I count from the far left, 1, 2, 3, there's my cutoff line. Since the cutoff line comes in front of the decimal, so the decimal point, whenever it's not written explicitly, is at the very end of the number. So since my cutoff line comes before the decimal, that means we need to use scientific notation. So I'm going to move the decimal so that there's only 1 digit to the left of it that is not 0. So 1, 2, 3. So times 10 to the power of 3, and our original number is bigger than 1. So that means that this exponent is going to be positive. All right, so let's add that in to our chemical equation so that we can go from having a chemical reaction to a thermochemical equation. So as a reminder, we're never going to write our value or our energy term as a negative 1.45 goes on. Okay. The reason for that is because writing our energy term on the product side takes care of the negative. All right, so that's our thermochemical equation. Okay, now we get to actually draw the potential energy diagram. So let's start that out. So our y-axis is potential energy, or its change in enthalpy. Then x-axis is reaction progress. Now, since this is an exothermic reaction, and how I can tell that is because our energy term is on the product side, but also I can tell that because combustion reactions typically are going to be exothermic. Okay, so what that means is if my reaction is exothermic, my reactants have more potential energy than my products. All right. So when you're drawing potential energy diagrams, you should always kind of have a bump to it. Okay. I would not recommend drawing diagrams like this just because they're oversimplified and they really don't show activation energy all that well, especially for exothermic reactions. Okay, so now what I'm going to do is I'm going to fill in my reactant and product plateaus with my reactants and products. Okay, I'm going to label the change in enthalpy. So the change in enthalpy is always between, or the difference between the reactant plateau and the product plateau. So negative 1.45 times 10 to the power of 3 kilojoules. Okay, and then last but not least, we need to make sure that we're giving this a title, so we're going to call this the combustion of methanol. Okay, so usually the title refers to what's happening in the reaction.
Are you from the cart, which means it would have to sit in the cart while it goes? Let's see.
All right, and that is it for this question here. Example number 2, we need to draw a potential energy diagram for the decomposition of potassium chlorate. All right, so for this one, it's going to be similar steps to the first example here. So if you wanted to pause the video and give that a try on your own, you can do that. So remember, you're first going to write a thermochemical equation. So that's going to require you to have the molar enthalpy of decomposition of potassium chlorate. From that molar enthalpy, you're going to have to find the change in enthalpy using this formula, but instead of the molar enthalpy of combustion of methanol, you're just using the molar enthalpy of decomposition of potassium chlorate. Okay, and then you need to figure out, okay, is it an exothermic reaction or an endothermic reaction? That's going to tell you whether to place your change in enthalpy on the reactant side if it's endothermic or the product side if it's exothermic. And then you can use that to draw your potential energy diagram when you have figured out if it's an exothermic or endothermic reaction, and then make sure to fully label your diagram. Okay, so you can pause the video, give it a try. I'm going to show my fully worked out solution in a little bit. Okay, so here for my balanced chemical equation, I've started off with potassium chlorate. How I know what chlorate is if you go to your periodic table, if anything ends in ate or ite, it's going to be a polyatomic ion. Okay, so chlorate can be found right here. That's a ClO3 with a 1- charge. So that's how I'm getting the chemical formula for this. Now remember that a decomposition reaction takes a compound and breaks it apart into its elements. So that's why I broke it apart into potassium, chlorine, and oxygen. Now remember, chlorine and oxygen are part of Hofbrinkel. So Hofbrinkel, that tells you all of your diatomic elements. So there's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So that means when any one of these are by themselves, not in a compound, there's always 2 atoms of them. Okay, so now at this point, I need to calculate my change in enthalpy so I can go from a balanced chemical equation to a thermochemical equation. All right, so now I've found my change in enthalpy using this equation. Okay, so how I got the value for the molar enthalpy of decomposition for potassium chlorate is I went to my data booklet, page 5 of it, and I found potassium chlorate here. Okay, so keep in mind page 4 and 5 are the molar enthalpies of formation. Now, since decomposition is the opposite process of formation reactions, we need to take this sign and flip it from a negative to a positive. So that's how I got positive 397.7 kilojoules per mole. So I multiplied that by 2, which is coming from the coefficient on potassium chlorate, multiplied the coefficient of potassium chlorate with the molar enthalpy of decomposition of potassium chlorate specifically. So remember, your moles and your molar enthalpy have to belong to the same substance. And I got 795.4 kilojoules. Okay, now at this point, I'm saying to myself, okay, it's a positive value. That means it's an endothermic reaction, and that means that heat is being gained by this system. So that means we need to put it as a reactant. Okay, now since this value was a constant, okay, we can never use constants to determine sig digs, so we're just gonna leave the sig digs here for now and just leave it as 795.4 kilojoules. All right, so there is my thermochemical equation. Now I can draw the potential energy diagram for this. So I'm going to label my axes. I'm going to have to scooch this down a little bit so I can fit in my title. So delta H, kilojoules, reaction progress, and since it's an endothermic reaction, that means my products have more potential energy than my reactants. There we go. So we got our potassium chlorates, which, as a reminder, whenever you have an ionic compound at room temperature, unless the question says otherwise, you can assume it's going to be solid at room temperature. All right, and my change in enthalpy is equal to positive 795.4 kilojoules. Okay, and then last but not least, I'm going to label this. This is just the decomposition of potassium chlorate. All right, so let's move on to activation energy and catalysts. So in order to understand how catalysts work and also how activation energy is involved, first we need to just get some background on something called collision theory, which basically explains how reactions happen. Okay, so collision theory states that reactant particles must collide for a reaction to occur. However, a reaction is only going to occur if you have the right orientation of your reactants colliding, and if you also meet the minimum amount of energy needed for the collision to result in a reaction. Okay? So without these two things, you won't get a reaction. Okay, and so that's why it's saying only a certain portion of the total amount of collisions that you have will result in an actual chemical reaction. Because if your particles or your reactants, when they collide, if they don't have the right orientation and enough energy, then a chemical reaction is not going to occur. Okay, now the minimum amount of energy needed in order for a reaction to occur, that is called activation energy. That is a term that you should know. Oftentimes it gets abbreviated to E with a subscript A. Okay, so all reactant collisions below activation energy will not result in reactions. Okay, now in order to make sure that a reaction does occur, oftentimes what chemists will do is they will increase the temperature, which is going to increase the collisions, which results in more reactions. Okay, so looking at this diagram here, okay, with this man rolling this boulder up the hill, in order for the spontaneous process of the boulder rolling down the hill to happen, he needs to put in enough energy to get the boulder to the top of the hill, and then he'll be able to let it go and it'll roll down on its own. Okay, that's effectively what activation energy is. Putting just enough energy into your reaction in order for your reactants to go ahead and carry forward with the chemical reaction. Okay, so from this top of the hill to kind of in line with the reactants, or in this case where the boulder initially starts out, that's where your activation energy is. Okay, so activation energy, you could think of it as how much energy your reactants need in order to get over the hill. Okay, so that a chemical reaction can proceed. Okay, so what we're going to do on this next page here is we're going to label where our activation energy, delta H, or change in enthalpy, and our activation energy for the reverse reaction are. Okay, so for activation energy, we're assuming that's for the forward process. We're reading this diagram from left to right. Okay, so we're starting at our reactants, we're ending up with our products. Okay, so how much energy you need to get over this hill from your potential energy of your reactants would be right here. So EA, and we're going to say forward. Okay, so that's from here all the way to the top of the hill. Okay, now for our change in enthalpy, that's just the difference in potential energy between your reactants and your product. So that's going to be here. And for this diagram, our change in enthalpy is negative. So I'm going to say change in enthalpy for the forward is negative. Okay, so again, where that is coming from is from here down to the potential energy of our product. So in between the potential energy of your reactants and products, that's where your delta H, or your change in enthalpy for your forward reaction, is. All right, now for the activation energy of the reverse reaction, the difference here is we are reading this diagram from right to left. So we're reading it in reverse to answer questions, or to get our activation energy for the reverse reaction. Okay, so again, since this is the reverse reaction, we're starting at our products and we're going to our reactants. So for our activation energy, to figure that out, you're going to start at the potential energy of your products and go to the top of the hill. Okay, that is your EA reverse. Okay, so as a side note over here, EA forward, you can calculate that by taking the potential energy of the top of the hill, which we will call the max, and subtract it from the potential energy of your reactants. So all I'm doing right now is I'm taking like what this applies to. So since EA forward is from here to here, I'm just taking the diagram version of what this is and putting it into a formula so that it'll make it eventually easier to calculate. So for our activation energy for the reverse, we'll be doing something very similar. So we're taking our max potential energy and subtracting it with the potential energy of the products.
Yeah, perfect.
Okay, now you probably noticed this label here of transition state. So transition state, all it is essentially the point in the compound where we've put in energy, so this energy right here, to break bonds. However, the new bonds haven't formed and released their energy yet. Okay, so the transition state is just something to describe we've broken the bonds in the compound, but we haven't yet formed new bonds. So that's what that is. Sometimes it's also called the activated complex. So also known as activated complex. All right, one last note before we move on. Sometimes you'll be given the change in enthalpy for the forward reaction, but then be asked what is the change in enthalpy for the reverse reaction. All you need to do is take the sign for the change in enthalpy of the forward reaction and just flip it. Okay, so if it's positive, you would flip it into a negative. Alternatively, if your change in enthalpy for the forward reaction was negative, you just flip it into a positive. Okay, so the first one was an exothermic reaction. Now let's label the same for the endothermic reaction. Okay, so the difference between the top of the hill and the reactants, that's going to be our activation energy for the forward reaction. The difference in potential energy from the products to the reactants, that's just your change in enthalpy. So a reminder that your change in enthalpy for endothermic reactions are going to be positive. So that's for the forward, I would say. Okay, and now if we're considering the reverse reaction and the activation energy for that. So remember, we're starting at our products, we're going to our reactants. So for the reverse reaction, we're reading this diagram in reverse. So this would be the EA forward, or sorry, this would be the EA for the reverse reaction. All right. So with catalysts, the whole idea about catalysts is that they're used to speed up reactions. So for example, it takes 3 years for a bottle of hydrogen peroxide to decompose. However, if you add in a catalyst such as manganese dioxide, then the decomposition of hydrogen peroxide only takes a couple minutes. Okay, so here we can see, if we look at this reaction here, which is in delta H notation, okay, there's no catalyst here, and the change in enthalpy is negative 145.4 kilojoules. But in this second version of the same reaction, we now have a catalyst. Typically, when you have a catalyst, you always write it over top of the reaction arrow. So let's just write that as a note. Okay, and the reason why catalysts go on top of the reaction arrow is because catalysts do not get consumed or produced in a reaction. Okay, now the key thing here is that notice the change in enthalpies. The change in enthalpy did not change when a catalyst is added. So the whole point of a catalyst is that it reduces the activation energy required for the reaction. However, it does not change the change in enthalpy. Okay, so catalysts reduce activation energy, which in turn helps speed up the reaction, but it does not change the change in enthalpy. Okay, so catalysts, because they speed up the reaction, it also causes the reaction to reach equilibrium more quickly. So equilibrium is a topic that we'll get into in a different unit. But once again, catalysts do not release or absorb any more energy. What that's saying is it's not going to change the change in enthalpy. Okay, so if we were looking at potential energy diagrams between an uncatalyzed reaction and a catalyzed reaction, this would be what it looks like. So I'm going to actually focus on this right-hand diagram. So the solid line is the uncatalyzed reaction, whereas the dotted line represents the catalyzed reaction. Okay, so the reactants and the products still have the same potential energy. That's why catalysts do not change your delta H or your change in enthalpy. However, what the catalyst does do is it reduces the activation energy required. Okay. So let's read a little note to ourselves. Because I've said a lot, but I just haven't written it down. So catalysts help reactions to happen faster and reduce activation energy, but don't change the potential energy of reactants or products Therefore, so therefore is those 3 dots. Catalysts do not change your change in enthalpy. Okay, so I'm repeating that quite a bit because it's an important point to know. All right, so looking at these potential energy diagrams here, okay, so once again, I'm just looking at the right-hand side. So notice that for the forward reaction, the change in enthalpy is negative 1,273.1 kilojoules. Now, if we were asked about the reverse reaction, okay, then this reaction would have a change in enthalpy of positive 1,273.1. So again, here, the only difference between the forward reaction and the reverse for change in enthalpy is the sign is just being flipped from a negative for the forward, flipped into a positive for the reverse. Now, talking about activation energy. So for the forward reaction, I'm going to look over here. For the forward uncatalyzed reaction, the activation energy is 120 kilojoules. Okay, so that's the difference from our reactants to the top of the hill is 120. Okay, but if we wanted the activation energy of the reverse reaction, so we're reading this diagram from right to left, okay, so this tells us that the change in enthalpy or the potential energy difference between the reactants and the products is negative 1273.1, okay? But that's if you're reading this diagram from left to right. Okay, so how I would read this to get the activation energy in reverse is we're starting out here, we gain 1,273 kilojoules of energy, and then we add another 120 kilojoules. Okay, so to get the activation energy for the reverse, we take the change in enthalpy for the reverse, which is positive 1273.1 kilojoules, and then we'll add another 120 because the positive 1273.1 only gets us from our products up to here, and in order to get to the top of the hill we need to add another 120. Okay, so the reason why I'm doing it this way where I'm adding instead of on the previous page where I said like, oh, you just subtract, the reason why I'm doing that is because we're only told what the activation energy for the forward reaction is. So we're only told this difference in energy. Okay, we're not told exactly what the potential energy of the top of the diagram is. So that's why I'm doing it a little bit differently than what I said before. Okay, so adding 1273.1 plus 120 is how they're getting the EA for the reverse reaction. Now for the catalyzed reaction, okay, once again, we're going 1273, no, that would be 1273 to right here, plus another 60 kilojoules to get the activation energy for the reverse catalyzed reaction. Okay, so we'll do an example where we're calculating out the activation energy for the forward reaction for the uncatalyzed and catalyzed reaction. So this is where we are going to be applying this formula. Forward is equal to max minus reactants, and EA reverse, that was max minus products. Okay. So for the uncatalyzed, I'm going to do that in blue. And for the catalyzed, I'll do that in purple. So I'm abbreviating uncatalyzed to uncat and catalyzed to just cat. All right. So the uncatalyzed reaction, that's this kind of green or teal line, whereas the catalyzed reaction is the purple line. Okay. So we need to just figure out, now that we have some numbers for our potential energy, we need to figure out where the top of our hill is. So this is about halfway in between 0 and negative 100, so I'm going to say that's negative 50 kilojoules, whereas this one over here, hey, that wasn't a very straight line. That one we'll say is about negative 275 kilojoules. Okay. For our reactants here, I'm going to say that's negative 575. And then for the products here, that's not very straight. I'll say that's negative 750. All right, so now that we have some values, now we can get to work on this. All right, so for the activation energy of the forward reaction for the uncatalyzed, we're going max, so that was at negative 50 kilojoules. Minus our potential energy of our reactants, which is negative 575. Okay, so effectively we're going negative 50 plus 575, which is going to give us positive 525 kilojoules. For our catalyzed reaction, we're going to go our max, so our max happens at negative 275. Minus our reactants, which is negative 575. So we're going negative 275 plus 575. That's going to give us 300 kilojoules. All right, now we're figuring out the activation energy for the reverse of the uncatalyzed and catalyzed reaction. Okay, so for the reverse, remember what we're doing is we're going the max minus the potential energy of the product. So the max for the uncatalyzed, that was negative 50 kilojoules, minus our products, we said, was negative 750. So negative 50 plus 750 gives us 700 kilojoules. For the catalyzed reaction, our max was negative 275. And then our products were negative 750. So negative 275 plus 750 gives us positive 475. All right. All right, for part C, what is the change in enthalpy of the forward reaction? So now that we have a diagram, the change in enthalpy is just the difference between the products and the reactants. Now, since this is for the forward reaction, to find the change in something, it's always final minus initial. So in this case, products minus reactants. Okay, so that's going to be negative 750 for our products minus negative 575. And these are both in kilojoules. So we're going negative 750 plus 575. That's going to give us negative 175 kilojoules. And then what is the change in enthalpy for the reverse reaction? Well, all we need to do is we need to take that negative 175 for the change in enthalpy of our forward reaction and just flip the sign from a negative to a positive. All right, so as a summary of catalysts, so you do need to know what catalysts are and what they do. So they speed up reactions, decrease activation energy, they don't change delta H or change in enthalpy, they are not used up in reactions, and all they do is they provide an alternative pathway which requires less energy for the reaction to occur. Okay, now some common catalysts to know, one of them is enzymes. So looking at the previous page, you may have seen catalyzed reaction and then in brackets enzyme. The enzyme is the catalyst. Okay. Other catalysts would be chlorofluorocarbons, sulfuric acid, nitric acid, and catalytic converters in cars. Okay. So you should be aware of some different types of catalysts, but the more important thing to know is what catalysts do and what they do not do. Okay, so they speed up reactions, decrease activation energy, but do not change your change in enthalpy, and they are not consumed in reactions. All they do is provide a different pathway for the reaction to occur, and that's how they reduce activation energy. Okay, and like I said before, if you are trying to communicate that there is a catalyst in your reaction, you just put it up above the reaction arrow.